All right, in this video, we're going to be going over our electron diagrams, and we're going to be able to write electron configurations and also write them in shorthand notation. Once we do it with the electron diagram, I'm going to go ahead and show you guys a shortcut where you could actually use the periodic table to write these electron configurations as well. So let's go ahead and get started. The question that I have is, what is the electron configuration for vanadium, and what is the shorthand notation? The first thing you need to know about vanadium is you need to know how many electrons vanadium has, because we need to know how many electrons we're going to be putting into the orbital energy diagram. So you find vanadium on the periodic table, and you see that vanadium has an atomic number. Vanadium has an atomic number that's 23. Now, this tells me not necessarily how many electrons I have, but this does tell me that my number of protons equals 23. Now, since this does not say that vanadium's an ion or anything like that, that means that we're going to assume that vanadium is neutral. So if it's neutral, then the number of protons will equal the number of electrons. Therefore, the number of electrons is 23. So I am going to be putting 23 electrons into my orbital energy diagram. Now, there's a couple of different rules that we need to remember. One of the first rules that we need to remember is that when we start filling in our orbital energy diagram, we're going to be starting from the lowest energy level and we're going to be moving up. So I'm going to go ahead and I'm going to start putting some electrons in here. So I'm going to go ahead and I'm going to put, there's 1 and 2. Now my other rule says that only 2 electrons can be per orbital. So each block right here represents an orbital. So now that this one is full, I'm going to go ahead and I'm going to move up to my next one, which is my 2s. 1, 2. That's filled. Now I'm going to go up to my 2p orbital. Now, if you look at the 2p subshell, we see that it has 3 separate orbitals. Hund's rule states that when we fill these, we need to put 1 electron into each energy orbital before we can double up. So just to remind myself, I always like to go up, 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 and down, down, down. And I discussed this in class, but one of the reasons why my arrows are up and down is that electrons have something called spin. And when we pair them up, we always pair up an up spin with a down spin. So I like to denote this with little half arrows pointing up and one pointing down. Now, if we count how many electrons we put in here so far, we have 2 in my 1s, 2 in my 2s, and 6 in my 2p. We actually have only 10 electrons in there. So I still have a few more. So let's go ahead and finish this up. So we have 10, and we're going to have 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So this is what it would look like when I would fill out my orbital energy diagram. I have 23 electrons in there, and you can see that I followed all my rules. Now we're going to write out our electron configuration notation. So I'm going to start with my lowest energy, so my 1s. So I write out my orbital, and it is a 1s subshell. And that superscript that's a 2, that tells me that I have 2 electrons in my 1s. Now we move on to my next one, which is 2s. So 2s, and there are 2 electrons in there. Move on, we have 2p with 6 electrons, 3s with 2 electrons, 3p with 6 electrons, 4s with 2, and 3d with 3 electrons. So this is my longhand notation for my electron configuration for this example. But now what we can do is we can also look for our shorthand notation. And our shorthand notation takes these and it says, what is my previous noble gas? And if you look at your periodic table, you see that my previous noble gas is argon. So I'm going to put argon in brackets, and that pretty much denotes what I just highlighted right here. So that argon denotes this, and then we could just fill in the rest. 4s2, 3d3. And so this is my shorthand notation, and I do denote that with the previous noble gas. Now let's go ahead and look at another way that we could possibly do this problem if you did not want to do a whole energy orbital diagram. Right here, what I have is I have a diagram of our periodic table, and it has labeled out the different blocks. So if we start over here, we see that these first two columns are called my S block, and it is 2 elements wide, which means that it can only hold 2 electrons, which we have seen. Right here is called my P block. We see that it's 6 elements wide, so that can hold 6 electrons. We have my D block right here, which holds 10, and my F block right here. Now, one of the things that I want to note about my F block is that this actually ties in right here. So this actually comes in right after the 6s. So if I were to label, say, starting from my 6s, I would go 6s, let's say 2, 4f, 14, 5d, 10, and then 6p6 if I want to go all the way through. So notice that I kind of go from here, swing through here, because I want to make sure I cover them all in order, go through here, and then go through here. So when I'm reading these, I read them off as you're reading a book. I'm going to go ahead and erase this, and I want to go to our example that we had. So vanadium actually ends up being right here on the periodic table. So if I were to try to figure out what my electron orbital energy diagram is, I would read this off from left to right, stating how many electrons are in each row until I got to my element. So if I start right here, I'm in my 1s block, and there are going to be 2 electrons in there because I'm going to go all the way through it. Now that finished my first row, so I'm going to go ahead and move down. Now I have my 2s block, and there are 2 electrons, and move over to my 2p block, which has, I almost wrote 3, it has 6 electrons. That make that a little bit neater. Move down, because now I'm done with that row. 3s2, 3p6, 4s2, and 3d3. So if you look at that and compare that to the one that we did previously, let me go ahead and scroll right back up here, you see that it's actually the exact same thing. So depending on what you're asked and what tools you have, you can use either one of these. Now, if you're not given the orbital energy diagram like we were given up here, this is our orbital energy diagram, it is a little bit easier to go ahead and use the periodic table method. And this is the method that I usually use when I'm doing these types of problems. So hopefully that helped you guys, and good luck.